Hello all. So now let's start with non-parametric spectrum estimation methods. So as the name suggests that due to this non-parametric name, it implies that they do not make any assumption about the data generation, and that's why it is called non-parametric. And the second thing is that all these methods are based on DFT, that is our discrete Fourier transform. So let me write it is discrete Fourier transform. Now, so these are the methods. First will be the periodogram. We'll be starting with this, then averaging periodogram, then Bartlett's method, Welch method, and at the end, Blackman-Tukay method. So we'll be discussing all of them in thorough detail one by one. So let's start with periodogram first. So first of all, what is periodogram? Right. So what is periodogram? Let's see that. So the spectrum, uh, the non-parametric methods, as we already said, they are based on the estimation of the Fourier transform of the autocorrelation. So basically, our first task will be to have the autocorrelation sequence of any given random process x of n, and after that we will take its Fourier transform. So let's start by this. So let's say we are given any process x of n. Let's say we are given any process x of n. Okay, and we have to find its autocorrelation sequence. So autocorrelation sequence will be, as I already said, let's say we are having a time lag of m between two. So there I wrote tau something in last lecture, so don't get confused. It's nothing much. So I'm just writing the same equation again. It's summation from minus n to n, x of n and x of n minus m. Or you can write x of n plus m for that matters. It doesn't matter. So now let's say this is our autocorrelation sequence and this is our actual autocorrelation sequence. So taking its PSD Fourier transform, that is our PSD, will be our actual. Okay, it won't be the estimated, but this will be our actual one, actual periodogram. And periodogram is nothing but just the power spectral density of its our Fourier transform, but it's little bit modified that we will see. Okay, what is modified? We will derive thoroughly what is periodogram. Okay, then I will get to perfect definition of the periodogram. So I am taking the entire route to have the definition of periodogram. So stay tuned. So now let's say if x of n, because as we already said, this will be our actual periodogram and this won't be estimation. But as we already discussed, in practical situations, it's not possible that x of n is not available. Let me write capital X of n for the process so that there won't be any confusion. So all these are capital because this is our random process x of n. So in practical situation, it's not possible to have the all data points. Okay, so the only finite segment of x of n will be available, as I already said in our last lecture. And due to that purpose and due to that reason, sorry, we can say that let's say x of n is measured over finite interval. We are just having a finite interval and it is measured over some interval called 0 to capital N minus 1. So then our autocorrelation sequence will be the estimation, right? So then it will be the estimation. That's why I'm writing hat over here. It will be estimation and it is given by 1 upon n summation from n equals 0 to n minus 1. Let me write capital X of n and x of n minus n. So it is nothing but the multiplication of two time lagged versions, sum over all the data points and just divided by total number of data points, right? So it is the estimated one because we are now restricting ourselves to 0 to n minus 1, that is our finite sequence. Now you can easily prove this. I'm not going to prove, but you can accept it without proof, that we know that Rx of m is symmetric, so it will be Rx of minus m. So the most widely used estimator, this is the actual one, not the estimator one. Okay, so the most widely used estimator, we can write the same thing for Rx of estimation, Rx hat of m as well. Okay, so we can write for hat as well the same thing, that for it will be from n equals 0 to n minus 1, x of n and x of n minus m, and it will be r x hat of minus m in just the opposite result. So it will be from 0 to n minus 1, and this will be from minus of n minus 1 to 0, and rest it will be elsewhere it is 0, right? So from this, in this range we will be having this, in this range, okay, this is m, the range will be of m and not of n, mind it, right? So now taking the Fourier transform of this, that is our estimated version, will give our power spectrum estimation, obviously. So let's take the Fourier transform, but basically we will be taking the discrete time Fourier transform, because since it is our discrete sequence, okay, mind it, we are not taking the DFT. There is a difference between DTFT and DFT. I hope you are all knowing the basics of signal systems and signal processing. Okay, so basically DFT is basically derived from DTFT by sampling it at particular frequency intervals, but that is not the topic of this lecture. Okay, for that you can see my previous videos. I have separate playlist for DFT. Okay, so let's continue now. So taking the DTFT, we obtained the estimate, and let's say it is denoted by the Ixx of n e power j omega. It is denoted by this, and this is the estimate of what? It is just the DTFT. So as per the definition of DTFT, I can write something like this: from minus n minus 1 to n minus 1 Rx hat of m e power minus j omega. Let me take the new page and write, sorry. So I can write Ixx, this is the estimator, okay. So the estimated PSD, that is power spectrum estimation, okay, is given by summation. This is the definition of DTFT, nothing else. Okay, so it is Rx of m, this is our estimated version, and e power minus j omega m. Clear? So we can now, can we do something on this first? This is our important result, so let me write it. Okay, let me write perfectly. Now we can express, this is nothing but our periodogram. Okay, slowly we are getting close to this periodogram. That what is periodogram? So this is basically our periodogram, and now we can express, this line is very important, that we can express the periodogram directly in terms of process x of n. How? Let's see. And in order to do this, we can to express this, we define, let's say define a length n sequence, and let's denote it by x n of n, which is obtained from our process, original process x of n. So it is obtained from our x of n as follows. So let's define this as follows. So let me write that x n of n, which is nothing but length n sequence, which is obtained from our original process capital X of n in the interval this, and it will be 0 elsewhere. Now this this equation can be mathematically expressed as, I can write x n of n as the process x of n and multiplication with some process w of n, and where w of n is nothing but a window, because suppose I am given any process, random process x of n. This is my random process x of n. If I will multiply it with a finite window from 0 to n minus 1, then what I will get? I will get this sequence, right? That we already defined, that from given x of n, we are just truncating it. You can say this. Okay, so we can say that this is where wn is. First, let me write the limit of n. N is from 0 to n minus 1, and the wn is nothing but a rectangular window. Okay, so now the estimated correlation that is we already wrote, I am writing again, that Rx of m can be written as 1 by n, its summation from n equals minus infinity to plus infinity. Now note that the limits are changed. Why? Because I am writing xn of n that we define in order to, and what, for what purpose we are doing all this thing? Just to express the periodogram directly in terms of x of n. For this purpose we are doing all this stuff. Okay, this might be confusing, but just bear with me. You will get all the things, I promise. So this is just the autocorrelation sequence of the process that we defined, the truncated one. Okay, so it's just a time lag. So this is nothing but a convolution, but not exact convolution. It is xn of m convolved with xn of minus m. Okay, so it is convolution, but it is convolved with xn of minus m, because the definition of convolution says that summation x of k, summation is from minus infinity to infinity, x of k and x of n minus k, right? Where k is from minus infinity to infinity, right? So same thing is over here, that our, sorry, n is from minus infinity to infinity, pardon me. So from summation n equals minus infinity to infinity, x of k and x of n minus k will define the convolution, right? But here it is totally opposite, that our, this thing is m, okay, and this thing is over here this. So basically the convolution is between x of n and x of minus m, right? So it won't be the convolution with x of n and x of n, but it will basically x of minus m. And now we will take the Fourier transform of this, which is our required PhD. So just taking Fourier transform of both the sides, what we can get is that our, the estimated spectrum, and it will be, we know that this convolution will leads to multiplication. So we can write something like this, that it will be raised to j omega, and from Fourier transform properties, the Fourier transform of this will be given by xn of e power j omega, and it will be minus. Okay, so this minus can be written as conjugate as well. So I am writing conjugate of the entire thing. Okay, so please note that both are capital letters. Just for the notation, this is a footnote, that for the notation purpose, here I am writing both as capital, but here the index is in time domain, whereas now in Fourier transform, after taking Fourier transform, so here we took the Fourier transform. Okay, so let me write here that taking Fourier transform, or we can say discrete time Fourier transform on both the sides to be precise. So basically we can write like this. So the next step will be, we know that multiplication of xn with its conjugate will result to its modulus square. So at the end we are left with our periodogram, which is given by ixx of n, because this is n point data sequence, so that's why I'm writing n, and it is given by summation of 1 by n, that is average, and it's nothing but this thing, just a DTFT, you can say that, just the DTFT magnitude squared, and it's divided by its total length of sequence will give me the periodogram. So we achieved our target. What was our target? Our target was, we need to express the periodogram directly in terms of x of n. So we did it. Okay, so let's see further things. So now using DTFT, because we know the relation between DFT and DTFT, so in terms of DTFT we can write something like this: 1 over n, it will be xn of k. In DTFT we are having the finite length. Okay, so it will be k, and then this will range from 0 to n minus 1. So a single statement can be written for this entire equation, is that the periodogram is nothing but, so here I comes the definition of periodogram, that the periodogram is the magnitude squared function of DFT, that is discrete Fourier transform now, not DTFT, of the data sequence, because we know that since we already truncated, that's why DTFT is converted into DFT, because we know that DFT is for finite sequence. So DFT of our original data sequence, or we can say our random process of the random process, that will be better, because we are now estimating, so we are in the domain where we are not having the actual sequence, but it's our random process, statistical processes. So that's it about this video, because the length is quite a bit longer now. From next lecture we will be starting with the consistency, how we will estimate. We have estimated our periodogram, so how consistent is that? Okay, all those things we will be discussing in our next video. Okay, so you can put this equation like this only in terms of e power j omega, right? And so this I can write as 1 upon n summation n equals 0 to n minus 1 x of n. I am just writing the definition of the Fourier transform, that's it, e power minus j omega n, and its mode square, so it will be square. So I am just substituting, okay, the x of n value, which is nothing but we know by the definition of Fourier transform. Okay, just don't confuse, because in discrete domain this is small x of n, right? But over here we are having the random processes, all these are WSS processes. Okay, that's why I'm writing capital, in order to distinguish between process and the sequence, right? So that's all about this video. Stay tuned. Thank you.